Good evening, everyone. Welcome back to NPTEL live session for week 8. So today's lecture is going to be totally dedicated towards the MOSFET spectroscopy that has been covered in week 8 lectures. I hope you guys have gone through the videos that have been uploaded by Professor. So is there any question from the previous lectures before I start the MOSFET spectroscopy today?
No question, ma'am.
Okay. So today we have to cover a lot of topics. As you can see, I have made 7 assignment problems that would be more or less from your whatever the concepts that I'll cover today. So that will help you to solve the assignment questions that have been uploaded there. And these are the topics that we are going to cover today. We'll try to cover it as much as possible because this is important to understand the MOSFET spectroscopy properly. So firstly, we'll start. Uh, if there would be any doubt at any point of time, you have to unmute yourself or put the question in your chat box so that everything would go in properly. Okay. So the last lecture was mainly we have covered the circular dichroism part, and in the last few minutes we started talking about the MOSFET spectroscopy, and related to that different kinds of spectroscopic techniques that we have, say for example NMR, IR, UV, MOSFET in that. So we compared that MOSFET spectroscopy, it involves a high amount of energy. That means it involves gamma rays. So this is a huge amount of energy. So we basically saw the difference that in case of NMR that works with radio frequencies, if we have a nucleus which is active, which is NMR active, so for example, we are taking I equals to half, I is nothing but the nuclear spin state. So this is the case that we can consider of a proton or 13C. 19F, 31P. So these are the different isotopes of different nuclei. So which would be active NMR active nucleus. So I'm considering a case of I equals to half. So in this particular case, we will see that two ml values would be there. ml equals to plus half, m equals to minus half. And in this particular condition, we will be ending up having, this is a case when there is no external magnetic field. We have understood this concept, like why the nuclei is going to have its own magnetic field which will interact with the external magnetic field and will process around it. Because of that, there would be an absorption of energy, and then when that frequency that we are giving, it matches with the transition energy between the two states. For example, here in the absence of external magnetic field, both the ml values, they are degenerate, they are having same energy. But in presence of magnetic field, external magnetic field, these both states will go in two different directions. Why is it so? Because there would be possibility that nucleus will go in alignment of the external magnetic field. For example, if I consider this up spin and the magnetic field direction is also up. So if this is a scenario, that would be one condition. If that is the opposite, like we are applying the magnetic field in this upward direction, but the spin of the nuclei is going down, so that's in opposite direction. That's the second condition. So that's why we get two different states, and corresponding to that, one goes at excited state and one goes lower to that what we were having earlier. So this becomes 1 by 2 and this is minus 1 by 2, as I've already told. Then in case of the magnetic energies or NMR, we have the energy already in negative value. So when I have put ml equals to half, the total energy becomes negative. So the more negative energy stays in the ground state, because lesser the energy, more stability is there. If energy is very high, that goes to the excited state. So this state becomes a beta state where it is opposing it. This becomes an alpha spin state, which is aligning it. So the energy between them, it is actually matching with the radio frequency range. So this is a delta E. And this delta E, so I was explaining that we have now, when I said that in absence of field, we were having both the ML values at a degenerate state, like they were having same energy. There was no splitting at all because both the spins can stay in one particular direction, one particular area. But when we are applying a magnetic field, because of their different alignment with that magnetic field, either they will be aligning with it or opposing it. We got alpha state and the beta state, and there is a delta E now. There is a difference of energy between the two states, and that difference of energy is actually dependent on the frequency and magnetic field that we are giving. So in case of NMR, this is a condition when the take home message here that in NMR, it actually the transition happens between ML values of the same I. That nuclear spin state is same, but the different ML values. So NMR, the transition happens between that, and it requires a radio frequency. But what if we have a very high energy? Very, very high energy actually. If we see that gamma comes at the top priority and radio becomes at the last. So this is having the minimum energy and this is having the maximum energy. So you can understand that earlier we were having a radio frequency range only. So the transition would happen between these two states only. But if I'll provide a lot or a huge amount of energy, that transition get go from ground state to the higher excited state. So that's why in this particular case in Morse-Bauer, this spectroscopy, it deals with the different nuclear spin states. Now it is no longer a same nuclear spin state. For example, now the transition could happen from 1/2 to 3/2, 3/2 to 5/2, or so on and so forth. So these are the conditions. It is not between the 1/2. Now it's a huge amount of energy, so it can cross that particular spin state, and therefore the changes could happen, and therefore we see the transition with the Morse-Bar spectroscopy. So that's a basic introduction regarding the Morse-Bar spectroscopy. Now, to explain it properly, for a Morse-Bar spectroscopy, we have one nucleus. Since we are talking about nuclear spin states, and this is another nucleus. Two and one. This is called source, and this is your sample. So what happens here? So if I'll draw energy, I have two parameters. So for example, in source, there are two I values existing. I equals to 3/2 and half ground state and excited state. So this is your excited state, this is your ground state. And in sample also, I have I 3/2. Why is it so? We are considering that nucleus 1 is equals to nucleus 2. That means source is equals to your sample. That's a general requirement for the Morse-Bar spectroscopy. So that why is it so? Because we are talking about the gamma radiations and the energy that is being lost. The same amount of energy has to be absorbed by the other nucleus. If they both are same, because that gamma energy is actually dependent on their nuclear states, and that is a property of that particular nucleus. So when nucleus is same, then only they will be able to take up the equal amount of energy, and the resonance will happen. If we are taking two different nuclei, that is also possible, but very rare cases, and research is still going on. So generally, when we talk with the Morse-Bar spectroscopy, the source which is going to give that radiation and the sample which is going to absorb that radiation has to be similar, more or less similar. So now if you'll see over here, we have I equals to 3/2. So the Morse-Bar, we have to talk about the two different spin states. So here, if you'll see, there would be some already we are talking about the excited state of the source, because if something has to emit some energy, that has to be an excited state. If it is ground state, that can't be having any energy, and so there won't be any emission of it. So if it is emitting some state, which I'm showing over here, so that is the transition, like whatever the transition is happening. And this energy, if I'm saying, that falls in a gamma rays, gamma energy, that is ER gamma. So it should fall on your ground state of your sample, and it should absorb, and therefore it should be able to excite to the same level. Because if I'm giving, if going from first step to the ground level, if we have to go from first floor to the ground floor, there would be number of stairs. So if the number of stairs that I have passed through, that is equals to 10, and the same number of stairs the other person is now going from ground to the first floor, that he or she will be reaching at the same time at the same flow, right? So similarly, if I am having a transition from the excited state to the ground state, it will release a certain amount of energy which lies in gamma region, and that energy, when falls onto the same nucleus, it will try to go from its ground state to the excited state. That's a basic principle, right? So that would be your E gamma, right? So, but actually, this is an ideal situation. We are talking about, okay, some source is there. It goes from, it comes from excited to ground. It releases some energy. Then it has been taken by the other nucleus, and it goes from ground to excited state. But actually, it does not happen in this particular way. So the E transition of that source is actually not equals to the E gamma, that the gamma radiations or the energy that has been lost. Why is it so? We need to understand that gamma rays are a huge, they involve a huge amount of energy. So whenever there is a huge amount of energy, what really happens, some of the energy gets lost in terms of recoil energy. What is recoil energy? Just take an example of a firing of a gun. If I am taking a gun and I'm firing it, the bullet is going towards in the upward direction, but our shoulder feels a push towards the backward direction. That's a opposite direction force. So this has happened when there is a lot of energy that we are with which we are striking something. So that's a kinetic energy, but in opposite direction. Similarly, when an excitation, that excited state has lost some energy, comes to the ground state, that's a huge amount of gamma radiation. And as soon as if it has to go to the absorber, firstly, some of the energy will take it back towards the backward direction. That's a kinetic energy towards the backward direction. So there would be a loss of energy. So in that particular case, when it is losing some energy, the E gamma that has been lost, that is going to be emitted, that would be less, because some amount has gone into the recoil energy. So this is your recoil energy. So this particular case, we are talking about the source, where it is emitting the gamma rays, emitting the gamma energy, but it is the amount which is like amount of the transition minus the recoil energy, because some amount has been lost in the opposite direction. Whereas if you'll see in the sample case, the case of sample, the E gamma would be E transition plus ER, because already the amount that is coming, now it would be taking it to a kinetic energy. Here also the recoil will happen, because the transition amount that has been required, that is now going to be distributed towards the transition energy as well as the recoil energy. So in case of the sample, it becomes a plus ER, and in case of the source, that is backward kinetic energy, that will be a minus ER. So therefore, there is a total difference of 2 ER. So recoil energy is the factor that does not let your source sample and source to have the to resonate. So if there is no equal energy, there won't be possibility of having a resonance between them. So the graph will look like this particular way. We have, since we are talking about the absorbance, so we are taking here absorbance, and here we have energy. Okay, so as we said that if this is the ideal situation, so my source will have certain kind of maxima here because it got drifted because of the recoil energy, and my sample would be the same ER over here. So if you'll see, there is no overlap or very negligible overlap. So when there is no overlap of the resonance energies, so when there is no overlap of the energies or the sample and the source, they are not having a common energy to be absorbed. Sample can't absorb that much energy, so there won't be any overlapping. Absorbance value would be 0, and the transmittance would become completely 100%. So in that particular case, if I'll see the graph for the Mossbar spectroscopy, we are not going to have anything over there. So the transmittance would be 100%. So what really happens if I have a source over here, if I have a source here and a sample here and the detector here. So detector has to detect some energy, some rays which are going to be transmitted. It can't be like if the complete absorption happens, okay, if X amount of energy is being released from the source and X amount of energy is being taken up by the sample, and there would be complete absorption. So therefore, no detection will happen because the transmittance becomes 100%. Transmittance and absorbance are inversely related to each other. So this case happens only when there is no absorption at all, when we have 100% transmitted. So whatever the absorption was there, there is no matching of the energy. So therefore, all the gamma rays are going directly to the detector. So that becomes a 100% transmitted. So in that particular case, we can't have any kind of knowledge about the nucleus of the sample as well as the source. So what we can do, there was a scientist, a PhD student actually, Rolf Mossbauer, who actually devised this spectroscopy and said that what if we this is happening because of the recoil energy, that some energy is being lost when we in the kinetic energy. So what if we are making our system to be stuck in a solid matrix? So what really does, took the nucleus and put it into a solid matrix so that it can restrict its motion. So that was a solid matrix or a lattice, you can say. Similarly, it happens for the sample also, because in both the case, it is showing the recoil energy, right? So in this particular case now, because of the solid matrix, the effective mass of the whole system would be very huge. So the recoil energy becomes very less. So recoil energy is now being given as E translational, that translation motion, plus E vibrational. Vibration is coming from the lattice vibration. So if at a case that because of the solid matrix, there can't be any transitional, so it becomes 0, and E vibration is being given as NH cross WI, where it is the N equals to 0, 1, 2, and so forth. H is your Planck's constant, and the Boltzmann constant, and WI is your frequency of the vibration. So at an ideal situation, ideal case, when we have N equals to 0, that time E translational and E vibrational both becomes 0. Therefore, ER becomes 0. So it is no recoil energy loss. So there won't be any loss of energy in terms of the recoil energy. So in that particular case, there would be too much of overlapping of the sample as well as the source. That means absorbance would be 100%, and we won't be able to see any signal in that case also. So in reality, we can't just have ER equals to 0. We can minimize it, but we can't have it 0 because there would be some kind of vibrations going on. So in this particular case, now the question is, when we are having the transition from I equals to half to I equals to 3 half, our curve looks like this way. So if I'll talk about the absorbance and here the energy, it goes like this way. So for example, it is I 3/2, it's I half, and this is line width that is width of half maxima. So that is the case. It is not giving you a straight line, that is coming as a Gaussian curve. Why is it so? The reason behind it. So we generally come across a principle called uncertainty, Heisenberg's uncertainty principle, where normally we take, so here that's a space, or we can call it as a position, that uncertainty in position, and this is momentum. Firstly, both uncertainties can't be calculated simultaneously, and their product has to be greater than equals to h cross by 2. Similarly, in this particular case, there are many pairs which exist in this particular form. For example, if we have delta E into delta T greater than equals to h by 2. So that is also one particular case. So these pairs are called as canonically conjugate variables or complementary variables. So what we are saying that here delta E into delta T is greater than equals to h cross by 2. So if I talk about this thing, excited state and the ground state. So this is the energy between the two states. And this is the half-life. And delta E, we can actually relate with line width also, which is tau. Delta E is equals to tau upon 2. That means we saw the line width over here. So it becomes tau upon 2 into delta T greater than equals to h by 2. If we cross 2 and 2, it becomes tau into. So now if you see that line width and the uncertainty in half-life, that is also comes under the conjugate thing, and therefore we need to have certain kind of line width. For example, if I'm saying that the question was that why the absorbance versus energy graph in case of the mass batch spectroscopy, it looks like a Gaussian curve, not a straight line. So if you're expecting it to be a straight line in absorbance and energy, that means here the energy is 0. So when energy is 0, according to this particular principle, uncertainty principle, the delta T becomes infinite. That means if my electron or the spin state or the electron is staying in the excited state, it will be there in the excited state for the infinite time, which is not possible. So there has to be a finite time up to which it can stay up to excited state, and then it has to come back to the ground state. So because of the finite time of the electron staying in the excited state, there would be finite energy level. And because of the finite energy level, the delta is not equals to 0. Because of the delta E is not equals to 0, and we know that it is related to the line width, that whatever the width of your peak is going to be, it is related to this particular format, and therefore we see this kind of Gaussian curve and not a straight line. Okay, now the next point that we have in mind is, so we talked about the line width. Now if I'll take an example of MOSFET active 57 iron nuclide, which we will take up in complete details. So here the transition happens from I half to I equals to I3 by 2 to I half. So in the excited state, the half-life or the tau value that we were talking about, the delta T, is 141 nanoseconds. So up to this time, it will stay in the excited state and then it comes back. So if I use this formula, I will be getting tau is equals to h cross upon delta T, which is 141 nanoseconds, and therefore it will give me value of 5 × 10⁻⁹ electron volt. And related to the any spectroscopy, we talk about the energy resolution also, how good your spectra is looking, how sharp your spectra is looking, because something regarding the resolution. For example, if I am having this peak and if I am having this much broad peak, and if certain changes happen, and because the area is less, the changes that happen, that comes under in this region and I can see that. But if the change so happen, it goes into this region only, because of the broadening of your spectra, you won't be able to see any kind of change. So we need a proper resolution. This becomes a high resolution spectra. When we have a sharp peak and small changes, you can see, you can observe all the precise information. So for the energy resolution, it comes from a certain formula where it comes as this line width divided by the energy. So if I'll say, for example, for 57 iron E, the E value for the excited state, it's 14.4 kilo electron volt, and tau we just calculated, it's 5 × 10⁻⁹ electron volt. So therefore your energy resolution, how your graph is going to be looking, so the energy resolution is tau by E, it would be 3 × 3 × 10⁻⁻13 electron volt. So you see that this value is very, very small. So if resolution is that small, if certain changes happen, you won't be able to see in the spectra, and we won't be having any conclusion for any nucleus. So how do we improve that? How do we improve our this energy resolution thing? So there are two parameters that affect or that can change the values of your energy resolution. So as I said, energy resolution is equals to tau upon E, that is the line width, and that is the energy difference between the two states, right? Now also we saw that line width we can't directly just say, line width is also related to your delta T. Delta T is the lifetime or half-life of the state, that particular state. So if you will see, if delta T is maximum, it goes to the denominator, tau becomes low. If tau is less, that means the line width is less, your energy resolution becomes less, because it is directly related to the numerator. So for that particular, for high resolution, the first factor that we require is the delta T, that half-life of that particular state, that excited state has to be less. It should not stay for a very long time at the excited state. It should come back immediately to the ground state. So the lesser the half-life, tau would be more and energy resolution would be more. So this point is clear?
Clear, ma'am.
No. So the first parameter is clear. Now the second thing is, if we have a very huge gap, the delta E is very huge, the transition that has to happen between the ground state and the excited state, that time also energy resolution becomes less. So when the states are having less energy, the ER would be, the energy resolution would be more, If they are having delta T less, that particular half-life is less, tau would be more, then ER would be more. So these are the main factors which would give you a high resolution, high energy resolution. And therefore, then you can have a precise information from different changes that are happening into your nucleus. Okay. Now we are going to, so up till this point, we understood that we started with the Mossbar spectroscopy. We talked about the gamma rays, that how much maximum energy they are having. And then we saw that it is actually involving the changes in the nucleus spin state, two different nucleus spin states. That also we saw. The next condition we see that in Mossbar spectroscopy, source and sample, we are taking them to be same because it has to be in a resonance of the energy being emitted and the absorption. Now, some energy we saw that it is going wasted in the recoil energy because of the high amount of energy that is being released. So some of energy is going in a backward direction. So the amount of energy that we are expecting to come from a particular source, it is not coming because some amount is getting wasted in its kinetic energy. So to have a low or no or less recoil energy factor, we put our system, the source and the sample, in a solid matrix so that there won't be any kinetic energy or a very less kinetic energy or a movement. And because of that, we got to know that we are having, okay, less equal energy factor. Now, source and sample could be having some kind of same energy for the absorption to happen. Then we saw that why our graph looks like this way, why it is having certain line width, why it is not this straight line, there is no line width, because this line width is dependent on this delta T. So uncertainty principle, which is making these pairs or position and momentum multiplication that comes under canonically conjugate pairs, which follow the uncertainty principle. And we saw that if we are saying that why our graph does not look like a straight line, delta E becomes zero. That means the excited state should have a very long life, like means infinite long life, which is not going to possible. It has to come back to its ground state after some time. So that's why the line width occurs. Then we talked about that what do we do for having a high resolution. So for high resolution, we saw that it depends upon tau divided by E. Tau is your line width and E is the energy between the two states. Tau is dependent on the delta T. That is your half-life, the lifetime of your states. So if half-life or the lifetime of your states is less, the tau value would be more, so resolution would be more. And if the two energy states are having less gap for the transition to happen, if this is less, then also resolution would be high. So these are the factors that we have taken so far. So is there any doubt before we start talking about the Mossbar spectroscopy, that active nuclear system? If there is any doubt, please ask the question.
Ma'am, less resolution energy solid matrix. So once again, explain, ma'am.
Okay. So at this point, we were actually talking about, okay, so this is a general case when we have a nucleus and when we have a source and a sample. So if I'm having a 10 electron volt unit, that from the excited state to the ground state, it will release a 10 electron volt. And I have a same nucleus, which have the same I states, I half and 3 half. Now I want the state to get excited from the I half to the 3 half. So it requires the same amount of energy, the 10 electron volt. But what really happened, because the gamma energy is a very huge amount of energy. So as we understood that when we are firing a gun, the bullet is going in an upward direction, but our hand or the shoulder goes in a backward direction because of the recoil energy. That means some kinetic energy is happening towards the backward direction because of the high energy and the mass. So what happens? Some of the energy gets lost in the kinetic energy. So that's why here we said that instead of giving that E gamma so lost, that is not completely that energy difference, that some amount has gone into the recoil energy, that is a kinetic energy. So in case of the source, the gamma rays that have been generated, that is equal to the transmission energy, which is having a loss in recoil energy. Some amount has gone to the recoil energy. Whereas in case of the sample, that some energy is now being given to the sample, which goes towards kinetic energy, that it starts moving. So therefore, now E gamma that it is going to absorb, that would be E transmission plus ER. So there would be some kind of energy difference because of the recoil energy, that kind of kinetic energy in the opposite direction. Because of that, the absorbance or the resonance does not happen because there is mismatching of the energy. So what do we do to have a minimum recoil energy or no recoil energy? So recoil energy is nothing but the kinetic energy. Kinetic energy is movement. If we stop or restrict our sample as well as source in a certain, like if you put a ball in a certain tight box where it can't move, so when the translation motion is being restricted, there won't be any movement and ball will not go anywhere. Similarly, source and sample, they were free, so they were having certain kind of kinetic energy and translation motion. But now if we take a solid matrix, consider it as a wooden block. So if I'm putting a particular source which was easy to move, now I've put it in a wooden blocks that it can't move. So the translation motion is stopped. So the recoil energy becomes very low, because as you can see, here is my nucleus, and the dots, that 4 dots have been made and the box have been made, that is representing a solid matrix. That is just a lattice. So somewhere we put it into a lattice or a crystal where it can't move, but there could be certain vibrations within that own lattice, because that is also made up of certain kind of phonons and that atoms are there. So because of their own vibrations, there would be some kind of vibration energy. Translation energy we can even consider as zero, but recoil energy won't be going to be completely zero, because it's a sum of translation and vibration. So we are taking an ideal case where translation becomes zero. Okay, there is no movement. But vibration energy depends upon n equals to 0, 1, 2 number of phonons that are present, that edge cross, that Boltzmann constant value, and the W is the frequency of that vibration. So even if we have restricted our source and sample in a certain matrix, there could be possibility of certain vibrations within that same matrix. Even though the matrix as a whole is not moving, but there could be vibrations. So that will give you little amount of recoil energy, but the amount of energy that was being lost earlier when they were free to move, that is not going to happen. And therefore, when we restrict our motion, when we restrict the motion of the solid and sample, we get some absorbance of the resonance between the sample and the source. That is where the recoil energy has to be limit down, has to be lower down. So is that clear now?
Okay, ma'am, clear.
Yeah. Okay. So other than that, is there any question regarding the things that we talked about? You understood the concept of the resolution and the source and sample?
Okay, ma'am, I understood.
Okay. So after 1 minute, I think you have to rejoin the same meeting link. So we'll continue. Okay. So now coming back to the main topic, which is our. So earlier what we talked about, that was the basics of the MOSFET spectroscopy. Now we are going to talk about the active nuclei, which are the active nuclei required for the MOSFET spectroscopy. Not all of them would be able to come into this category, the way it happens for the NMR system. In NMR also, when we say we have a condition that I value can't be 0. If I value is 0, that kind of nuclei can't give us the NMR spectra, because the number of neutrons and the protons are equal. So they cancel out each other's effect. There is no magnetic field anywhere. There won't be any magnetic field. So if there is no magnetic field, there won't be interacting